Okay, hello everyone. My name is Alexandre Champagne-Ruel, and I am a physics PhD student at the Université de Montréal. And thank you for having me at this session in universal biology. So today I'm going to be talking about cooperation. So let's start right away with my take-home message, which is that the emergence of life could have been favored by a cooperative takeover in prebiotic systems, whereby cooperative takeover we mean the rise to a predominance of reactive or minimal information processing cooperating strategies in a Darwinian setting. So let's look at the roadmap towards that conclusion. First, I'm going to be talking about cooperation, and especially at the microscale. Then I'm going to present a model we can use to investigate cooperation in Darwinian environments. And finally, I'm going to be discussing some of the results we get using that model and how do they apply to the origin of life. So you might be wondering at first, why cooperation exactly? But pick your favorite origin of life model, be it the RNA world hypothesis, hypercycle, autocatalytic sets, or the hot spring hypothesis, or even the major evolutionary transitions theory. They all assume some form of cooperation between replicators or network of molecules. So we define cooperation as mutually beneficial joint interactions between agents. And investigating cooperation is one of the objectives of game theory. Now, game theory can also be considered at the microscale. And in fact, a lot of people have used game theory to investigate the behavior of RNA viruses and proteins. And in fact, Yeats even introduced the term chemical game theory, where we could consider cooperation to be a behavior beneficial to the chemical field of the participating networks. Now, one important result in evolutionary game theory says that if you mix cooperators and effectors in the same system, some cooperating strategies can actually invade the system. But that result is only valid for systems where the fidelity of interactions allow the interacting entities to do so without any error. So in other words, errors usually impede cooperation. Now, in the context of the origin of life, one thing that we think we know is that the environments that are thought to have favored life were far from being in equilibrium. So going back to game theory, the stochastic environments would thus mean that players make random errors in gameplay. So the question then becomes, in those stochastic environments, how can we explain the emergence of cooperation in the context of the origin of life? So one way we can investigate the emergence of cooperation in such environments is through the use of numerical models based on evolutionary game theory. So there's this model in game theory called the prisoner's dilemma, which is used to highlight the tension between, on one hand, selfish and regional behavior, and on the other hand, altruistic cooperation. It's defined as a score matrix where two players, without knowing in advance their opponent's strategies, can either choose to cooperate or defect. Now, although exploiting your opponent yields the highest score, the average score is higher whenever one cooperates. And of course, this leads to a dilemma between two situations. One where one player wins it all, and another one where the group is more successful. Now, to assess the repeated interaction between players, and in the context of the origin of life, you can think of this prebiotic soup, where one species molecule would meet repeatedly with other molecules, is to use the iterated version of the prisoner's dilemma. And players that play the iterated prisoner's dilemma can implement strategies. You can choose to always cooperate or always defect. You can choose mutual cooperation, which is the reactive strategy called tit for tat. Or you can just play it random. By the way, the color coding you see on my slide for strategies will be used throughout my presentation. Now, another element that has probably played a key role in the emergence of life is the spatial distribution of molecules, which is why we have implemented our model in a 2D Cartesian lattice with periodic boundaries, where agents are initially distributed randomly at each site. And at each new iteration of the model, we let every strategy play the iterated prisoner's dilemma against every other strategy under more neighborhood. And then for each site, we replace its strategy if one of the neighbors has a higher score. Now, we have mentioned that in the context of the emergence of life, the environments were probably subjected to stochastic perturbations, which is why we have also implemented an error rate in the interaction with players. And by varying this error rate, we get very complicated dynamics, predator-prey and limit cycles, spatial pattern formation, and attractors in the phase space of the system. On your left, you can see the temporal evolution of the population frequencies for each species in the system, while on your right, you can see the final lattices or a sample of the simulations with varying error rates, which highlights this extreme sensitivity of the model to some parameters such as the error rate. Now, getting closer to a Darwinian environment, we can also make the error rate of agents heritable. On your left, you can see the final population fractions for a statistical ensemble of simulations with varying error rates. By the way, note the horizontal logarithmic axis on that figure. When the error rate is very small, we recover this domination of cooperations I mentioned before. Whereas when you increase the error rate, parasitic entities have the upper hand. But if you make the error rate of agents heritable, on your right, you can see that there's a general increase in the population frequencies of cooperating entities, which is in itself an interesting phenomenon. It means that including heritability in a system based on evolutionary game theory actually favors cooperation. But the most interesting result comes when we also include variability in the system. In other words, when we make the error rate of agents subjected to mutations. So now that we have included in the system this triad of evolutionary biology, of selection, heritability, and variability. On your left, you can see that TFT now invades the lattice for a wide range of error rates. Now, if you vary this mutation rate itself, on your right, you can see that there's a clear threshold above which TFT always invades the lattice. And by the way, note the horizontal logarithmic axis here, so actually the transition is quite sharp. And this behavior goes on until very high mutation rates, until a breakdown occurs at mutation rates close to 1, which is reminiscent of the eigenerror threshold in biology. But from a physicist's point of view, this transition is also reminiscent of something well known in physics. We have a complete and sudden spatial reorganization of the system, which goes hand in hand with a decrease in the error rate of TFT agents. We also have large fluctuations when we cross this critical point, and as you can see on your right, fluctuations are at a maximum when the derivatives of the populations are at their highest in this transition towards cooperative behavior. Now, in addition to sharing characteristics of phase transition phenomena, this cooperative takeover that we see when including selection, heritability, and variability in a system based on evolutionary game theory is a prime example of an emergent phenomenon. What we are seeing are novel features on the global or microscopic scale that cannot be directly inferred or predicted, even with a complete knowledge of system dynamics and interaction rules at smaller or microscopic scales, where the Darwinian dynamics should by all means favor selfish behavior. Now, faced with stochastic perturbations, the system reorganizes itself spatially, favoring cooperative behavior over a wide range of parameter values, which suggests that our results are not contingent on any specific implementation of a model and could apply to any Darwinian system faced with stochastic perturbations. Now, the last thing I want to mention about this cooperative takeover is the key role that mutual cooperators play in the process. This is interesting because TFT, while one of the most successful strategies at the prisoner's dilemma, is also one of the simplest strategies to encode, which could thus readily allow its emergence in nature through evolution. And TFT, while also being one of the simplest reactive strategies to the prisoner's dilemma, so it only cares about the last move of its opponent, so only one bit of information. It is one of the simplest, so in other words, it is one of the simplest strategies to react to the behavior of its opponent, to process information. And in the context of the origin of life, this emergence of information processing capabilities can actually bridge the gap between lifeless molecules and complicated self-replicators that encode their own replication mechanisms. Now, to answer that question, we must verify whether TFT can indeed arise spontaneously in the system without being pre-programmed, which is why we are now working on a model that includes off-field networks as learning machine analogs of prebiotic networks to verify whether TFT can emerge spontaneously by natural selection in physical systems. So I'm going to finish with that. Those are the main conclusions that we derive from our model. And I just want to mention very briefly this Origin of Life Digest that I publish every week on my website that you can subscribe to, which is a recap of the papers just published for that week on the Origin of Life. And OLEN, which is the Origin of Life early career network that I am part of, and which will hold its next meeting